In this section, we're going to talk about electronic systems, and the first element we need to consider are diodes. So diodes are a semiconductor, and semiconductors are typically from group 4 of the periodic table. So think back to your chemistry class way back, and group 4 of the periodic table's got your silicon, your germanium, and your cadmium. Well, cadmium sulfide's not in there, that's a combination, but in that grouping are things that we're going to put into semiconductors. And we're going to make things that are shown in the picture here. We've got an LED, which is a type of diode. We've got a PDIP package, which is a plastic dual inline package. It's just that little centipede-looking thing there that's got all the legs on it. But how does a diode come about? Well, if we have silicon makes a crystal, and so in pure silicon, which we never really have pure silicon, but if we had pure silicon, we would have a crystal with our silicon atoms hanging out there, and it's going to join, each atom's going to join with 4 other atoms, and so all of our electrons that form the valence shell of the silicon are all accounted for, they're all in use, they're all neutral, for lack of a better word here. So what we're going to do in a semiconductor, though, is we're going to look at the holes where an electron should be but isn't. And those are going to be considered as a positive charge carrier. So in our traditional view of charge, or in our traditional view of current, rather, we're looking at a positive flow, which we know is wrong because we know it's actually the electron flow. But we're going to look at the holes, and we're going to call that a positive charge carrier. So as current flows, it's actually holes moving around where the electrons have moved out of. So if we dope, which is to say we're going to take our silicon and we're going to remove one atom of silicon and we're going to put in something else, and that thing we're putting in is our doping. So if we dope with a donor element like arsenic or phosphorus, we're going to put that in, then we end up with a different number of electrons. Think back to your chemistry, different valence shells, different number of electrons. So when we do this with what we call an N-type or a donor element, then we have this extra electron floating around. And so we've got this wandering negative charged thing, which is the N-type doping. We could do it the other way. We could do a P-type where we put in something with an acceptor element. One extra hole is floating around now. We've got one fewer electron than we should have. And so with that one hole floating around, we've got this floating positive charge, and that's our P-type. So in a larger sense then, that's the element sense, in a larger sense, we're going to take this N-type and this P-type, and we're just going to jam them together side by side. And so when we do that, then in one of them we've got extra holes, which is to say extra positive charge in the P-type, and in the other type we've got extra electrons or extra negative charge in our N-type. And when we put them together, we get this sort of mixing that we call a depletion region. And so in the depletion region, the junctions in the middle of the depletion region, is where it's the extra charge on one side and the extra hole on the other side. They're going to kind of reach an equilibrium. And so that naturally sets up our anode and our cathode. And we've got these extra holes, we've got our extra electrons. And when we put these together like this, we call a single p-n junction a diode. So it's going to look like this in our standard circuit diagram. It's going to be a little triangle with a line on one side, and the anode is the back side of the triangle, and the triangle points towards the cathode, and that is typically our direction of current flow. So there we go. A p-n junction is a diode, and this is based on taking our silicon, or whatever we're starting with, but usually silicon, and doping with donor or acceptor materials. What does a diode actually do? Well, it's kind of the electronic equivalent of a check valve. So if you put current in, and you put it in the wrong way, nothing happens, at least to a certain extent. But if you put it in the right way, then the current flows. Now, just like a hydraulic check valve, if you're putting in current the wrong way, against the spring in this case, and you put in enough, it's possible that you could damage the whole system and then current would flow. And we can do the same thing in a diode. There is a certain region in which if you push too hard, you break it. But if you operate within standard limits, current flows one way, but not the other way. It's a check valve. So we can graph this, and we will graph this in terms of the voltage across the diode compared to the current through the diode. So it's going to look something like this. At really, let's see, so VD is our standard positive voltage in the correct direction. VZ is going the reverse. So if we apply a voltage and we get past a particular limit, Vy, then lots of current flows. If we're somewhere between Vy and Vz, which is our reverse limit before we break the whole thing, no current flows. And if we go lower than Vz, we've pushed current the wrong direction, it'll go ahead and it'll flow the wrong direction. So we call that wrong direction the reverse breakdown region. In the correct direction, where we've exceeded our initial threshold and current starts to flow, we call that the forward bias region. And in the middle, we call it the reverse bias region. So, mathematically, if VD is greater than Vy, which is somewhere on the order of 0.6 or 0.7 volts, then the diode conducts like a short circuit. If VD, the voltage of the diode, is between Vz and Vy, then it's an open circuit, there's no current flow. And if you're in the Vz region, then you're damaging your diode probably, unless you're dealing with a ZENER diode. So there we go. That's how we write up our diode in terms of the voltage and the current. Note the 0.6 to 0.7 for the Vy voltage. We'll see that again. So if we put a diode in with a voltage supply Vn and a resistor, and you have an input voltage greater than Vy, then what you're going to see is you're going to have a short circuit, and also that Vy, because we do have that 0.6 or 0.7 voltage drop across the diode. And so we get current flow that way. If we're the other way, we're between Vz and Vy, we're in our reverse bias region, then it acts like a short circuit and there's no current flow. It's an open, sorry, not a short circuit, it acts like an open circuit, no current flow. It's just sitting there with nothing going on. There's our open circuit. Also, we need to watch out for the current. We don't want to cook this thing like so many other things. If you put too much current, you can cause excessive heating and then it breaks down. So we would want to have a supply voltage and a resistor, a current limiting resistor, so we can limit the amount of current through the diode and make sure that we don't exceed the maximum. Now, how much is the maximum? You'll have to check your spec sheet for your particular diode. It's typically fairly high, but we do want to be careful with it. So what do we use diodes for? Well, we can do signal processing. So if you think about our sensors, which is typically what we're going to be caring about in this class, if you think about our sensors, we might have a signal that comes in that is modulated, like an amplitude modulated signal coming off of an LVDT, in which case we would need a diode for rectification to be able to translate that amplitude modulated signal into something that we can use. We might also want to clip it so that if we know that our voltage coming off of a sensor is somewhere between -15 and positive 15 volts, but we know that our next element in the sensor system can only take a -10 to positive 10, we might want to clip at those limits so that we don't damage the next element in the series, and we can use some diodes for clipping. We can also do peak detection if we want to just know, what was the maximum voltage that we saw. Well, we can do that with peak detection with a diode. We can also do voltage regulation. We can do indication with an LED to say, yes, this thing has happened, or no, it has not. And we can do system isolation, where if we have high voltage on one side and we need to isolate that from everything else, we could use something like an LED with a photodiode, and I'll show you an example of that, for isolation of the system. So let's look at rectification first. If we've got a AC voltage supply, VAC there, and a single diode with a load resistor, then we're going to call this a half-wave rectifier. So if we put in that VAC, it's a sine wave going in, then remember that as long as we don't exceed our limits VZ, or don't exceed the lower limit VZ, then in the positive side, we're going to act like a short circuit, And in the negative side of VAC, then we're acting between VY and VZ in our reverse bias region, and so nothing conducts and there's no flow. And so consequently, there's no voltage drop across the resistor or load. So we see only the positive section. You can also see there's a gap at the peak there between the blue and the red. Well, that's about 0.6 volts, which is the drop across the diode. So in this case, we've taken only the positive section and we've neglected the negative section, and that's a half-wave rectifier. If we make a bridge rectifier configuration here with 4 diodes, and you trace out the current, what you're going to see is that all of the positive stuff stays positive and all the negative stuff gets folded up around the axis so that everything is positive. So this is what we use for amplitude modulated signals. If we've got an AM signal coming in, we're going to first fold it up and then we're going to average it, and that'll give us our AM signal. Well, demodulated signal. But that's rectification, half wave and full wave rectification. We'll need these for various sensors. We can also clip if we've got an input and we know that it's going to be too high for our at the next system in the series, then we can always clip it. If we know that it's going to be consistently too high, then maybe we should be using an amplifier and reducing the gain. But if we know that we just occasionally have spikes that are too high, we could clip. So we've got our input, we've got 2 diodes, one going each way with a voltage supply, and so the one going down towards ground there is going to clip at the top, the one going up towards our input is going to clip at the bottom, and so the output of this is going to only reach the VM and negative VM voltages. And so if we clip this, we can make sure that our voltage limits are not exceeded for something like an analog to digital conversion. If we know that we've got sensitive electronics to protect, we can make sure that we do by never exceeding their voltage limitations. If we want to do peak detection, we could just use a single diode with a capacitor. Remember, the capacitor is going to charge and it's going to stay charged for a little bit. It takes a little while to dissipate. And so what we're going to see is that the diode will allow us to go up towards the peak, and then the capacitor will hold that value for a little bit. And so we can kind of trace out the peak instead of tracing each up and down here. We're just sort of tracing the peaks. Now, Zener diodes are a little different. They're a special type of diode that likes to operate in that reverse breakdown region. So instead of operating in the forward bias region, we'll operate in the reverse breakdown region, and it'll take advantage of a really steep and really consistent reverse breakdown. And so notice that let's see if I can draw it in with the pen here. Notice how in this region, that's a terrible drawing. Let's try that again. In this region, it's very steep, and it's very consistent that even as the voltage across the diode changes, it doesn't change very much for any of the current values in there. So we can pump a lot of current through and stay very consistently near VZ. Well, that's practically a voltage regulator. So that's one of our things that we'll use it for. We can model this as 2 parallel branches, one that's forward biased and one that's reverse biased, although we'll typically only use the reverse biased for the Zener diode. And so if we put it in something like this, where we've got a supply and a supply resistor and then a load resistor, well, we've got an unregulated supply, we've got a voltage regulator in there, and remember that the voltage regulator, no matter how much current we put through it within limits, is going to stay very close to VZ. So if we choose that our load current is going to be VZ, because it's going to stay very close to VZ and it's in parallel with the load resistor, so the load current is going to be VZ by RL, which is just Ohm's law, then we know that the load current coming from KCL is going to be the source current minus the current through the Zener diode. Then the source current must be Vs minus Vz over Rs, which is, again, just Ohm's law based on, well, it's Ohm's law and Kirchhoff's law combined. Then we can look at the total power dissipation of the Zener diode and make sure that we choose one that's got the right specs. So we can say that the power dissipation on the Zener diode will be whatever maximum current that we're dropping through it, and we can get that from KCL and our previous Ohm's law, multiplied by VZ. So we can always pick a Zener diode such that this will be regulated, that as we have our source and our load resistor, that the load is going to stay very well fixed at VZ, and we're not going to cook our Zener diode. So that's one useful application. Is it the only way to make a voltage regular? Absolutely not, but it's one way to make a cheap one. Yeah, like I said, we need to make sure that IZ, the current, is not too high or we'll cook it. So if we want to combine that Zener diode with a bridge rectifier, then we can make a DC power supply coming from an AC supply. So if we start with AC voltage in orange there, and we step it down, which is to say we're going to reduce its amplitude through a transformer. So we get it down to the right range that we want. We take it from 120 down to 5 or 10 or 15 or whatever we're dealing with. We put it through our rectifier, which remember is going to fold it up so everything is positive, like our gray. We can put it through a low-pass filter that'll act as a bit of an averaging here. So it'll kind of take kind of like that peak detection that I showed you. It's just going to kind of take it towards the top. It's going to take out a lot of that ripple. That's our low-pass filter. And then we put that through our Zener diode regulator. Well, that's going to smooth it out much more nicely, and because we've already taken out a lot of the ripple, it's going to be nice and smooth there. And then what the load sees is just a nice DC output with a little bit of a transient at the beginning, but certainly the transient at the beginning is not terrible. So there we go. We can make a cheap DC power supply, well, an AC to DC converter, kind of like those wall warts you plug in to power your router or your speakers or even your laptop. Although realistically, you're going to be using a different configuration in there, but this is one way it could be done. Also, we've got LEDs, which are light-emitting diodes. When they're forward biased, they're going to show a light. You've seen these before. And the intensity of the light is related to the current flow. So there's lots of different types, lots of different shapes and whatnot, but they're all the same sort of thing. Excuse me, they're just a diode that gives off light. So we can use it to indicate a value. If we say, boy, I want to show a light when this is true, it's just a matter of having a switch that's controlled by that statement, that if this is true, and then when we close the switch, it lights up. Now, it's always going to have the same voltage drop for the same LED, somewhere between 1.5 and 2.5 volts. It's going to depend on the color, it's going to depend on the size, it's going to depend on the manufacturer. Your red ones that we have in the lab are typically like 2.1 volts. And you're going to want a current limiting resistor so that you don't put too much current through the LED. If you put too much current through the LED, it'll cook. So we choose something just based on Kirchhoff and on Ohm. We can calculate for the maximum current or the maximum power dissipation for the LED how much resistance we need to keep it under that limit. And again, your limits are going to be in your spec sheets. A good rule of thumb is around 300 to 330 ohms for a 5 volts source in most of your LEDs. Some of your LEDs are going to be a little stronger, so maybe you can go down to 150, but 330 is a good spot to start. Photodiodes operate the opposite way. When you shine a light on them, then you're going to get a little bit of a current. So if we shine a light on this, we're going to get a current through the resistor RS. Looks like an LED, doesn't it? But it's a photodiode. So if we pair those up, a photodiode with an LED, then we get what we call an OPTO-ISOLATOR or an OPTO-COUPLER, which connects two circuits without actually physically electrically connecting them. We're going to put current through the LED. It's going to shine a light onto the photodiode, which is going to generate a current. So they're coupled. It's not going to be great for analog. It's going to be better for digital, where you simply want to know, is it on, is it not on? But it does provide a nice connection. So if you're dealing with high power on one side and low power on the other side, then you don't have to worry about noise being coupled through your ground lines or anything. They're fully separated. So there we go. Input on one gets an output on the other. Apparently that's all I've got for diodes, so we will pick it up next with transistors.